All right, so we're going to talk about different types of solids or types of solid structures. All right, so obviously everything that turns into a solid falls under one of these categories. All right, now a type of solid can be broken down into two main groups. We have crystalline solids and amorphous solids. Okay, a crystalline solid, that's just a regular arrangement of their components. It's like a regular table salt, that makes cubic crystals. Sugar, you have sugar crystals. Yes, even water, solid water can form a crystalline solid. So that's most of the solids you see are some sort of crystalline solids. Okay, the other type of solid is amorphous. Okay, amorphous, there's a disorder in their structure. So that is when the molecules just kind of form together in no set arrangement. Usually that's large organic molecules. All right, so those molecules are so large that when they cool down, they're just too large to arrange themselves in any sort of structured order. So anything like fat molecules, those are amorphous. Grease, thick oil molecules, okay, those are amorphous. When they solidify, they just turn into some gloppy mess with no semblance of order in their structure. Now, the crystalline solids we can break down into four different categories. Here's two of the four different categories. Okay, the first one is an ionic solid. Okay, an ionic solid, so it contains ions at points of the lattice that describe the structure. All right, so this is kind of the crystal you're kind of looking at. So some right here. Now, there are different types of shapes of crystals. And there's cubic, rhombic, hexagonal. Don't have to worry about that for the AP test. In addition to face-centered cubic, body-centered cubic, terms like that. Okay, that's not on AP, so that's something you'll learn in college if you move on from there. Really, here's how an ionic solid works. All right, so sodium tends to form a positive ion. Chlorine is negative, so you have your attraction there. All right, well, just like two magnets. If you take two magnets, put them together, they stick together, just like how sodium and chloride would work. But those two magnets, they're already stuck together, they can still stick to other magnets. You can build off of that. Okay, well, same thing here. You can do a sodium here and a chlorine there, another sodium here. So you see it goes on and on and on. You can do this. I can do this forever and ever and ever, but I only have so many gigabytes on my computer, so I'll stop here. All right, so there you go. So it just kind of keeps building on. And that's how you get your crystalline solid, or your ionic solid, just different negative and positive ions bonding together. All right. And again, it's all ions, so it's metal and non-metal. So sodium chloride, copper 2 sulfate, magnesium nitride, anything where it's a metal positive ion and a negative ion. Now, second type of solid is a molecular solid. All right. This is what we talked about before. The LDF, the hydrogen bonds, the dipoles, those are all the intermolecular forces for molecular solids. So they'll still form a crystal with their positive ends and negative ends, but what they'll do is they'll be attracted towards the positive and negative ends of those polar components, those polar molecules. So sucrose, like sugar, that's a molecular solid. Ice is a molecular solid. And yes, they will form crystalline structures. If you look really, really close, like in a microscope, you can see that these molecules actually form different types of set crystals. So that's a molecular solid. And again, it's all molecules, all nonmetals. All right. So if you see a metal in there, not molecular. All right. So that's your ionic, and that's your molecular types of solids. All right. So next to a little more specific here. Next one we call a network solid. All right, so think of a network solid as a giant molecule. So really it's all covalent bonding. So there really is no force of attraction like a dipole or hydrogen bonding or LDF. It's all sharing of electrons. And diamond is your best example there. So if you look at diamond, remember diamond is pure 100% carbon. Remember, carbon has 4 bonds to it. Well, if you take those 4 bonds and add some other carbons, and then each of those, you have more carbons to that, and more carbons to that. So same thing, you go on and on and on. And that's kind of what this here is. So this is your carbon, and carbons keep bonding, right? Now, that means these are shared electrons. So it's not just some attraction of a positive at one end of the molecule and negative at the other end. This is an actual chemical bond. It takes a lot of work, a lot of energy to break those bonds, a lot of heat to break those bonds. So that's why they're so tough. Yeah, that's why they say diamonds are some of the strongest compounds or strongest substances in the world. And it's because you really can't break those. It take a lot of work. So diamonds are pretty tough. And yeah, that's why we call it a giant molecule or a macro molecule, because technically they're all covalent bonds, so it's technically one big molecule. So yeah, so you give your special someone that diamond ring, you're really just giving him or her a molecule of carbon molecule. So not as romantic when you say it that way, but technically it is. So mainly carbon silicon based. So if you see a formula that has carbon or silicon in it, yeah, good bet that that is a network solid, because carbon and silicon both have those four bonding sites, so they can just kind of build off each other like that. They do not conduct heat or electricity, because the molecule or the electrons are all set in place there. They really can't vibrate as much or move around. So it's not a good heat or electricity conductor. This is another example of a covalent network. This one looks a little bit different. If you look at silicon dioxide, so if you sketch just a single molecule of silicon dioxide, yeah, it looks something like this. But if you look at the solid structure, what really happens is, with the oxygen, instead of these double bonds, the bonds will, one of those bonds will pop off of the one oxygen and hook to another silicon. So you have something like this. All right, so as a covalent solid, this is your silicon dioxide. So if you see anything like this, where it's a nice repeating structure with all covalent bonds, typically silicon based, typically carbon based, yeah, it's a network solid. So those are your network solids. Right. Now, why is quartz and sand much stronger than glass? Again, both of these are technically network solids. Why do you think they look a little bit? Why do you think quartz, which is on the left, why do you think that's a lot stronger than one on the right? Yeah, if you look, this is a lot more ordered. This looks a lot more kind of jumbled up. The bonds are, got stronger bonds down here versus here. Got a lot of these open areas. This just looks a lot more, for lack of a better word, looks more disorganized. Right? So that's why glass, even though it is a network solid, it's just really not as strong. So that's why this breaks these a lot more brittle, right? Because it doesn't have the set strong structures like quartz does. All right, so the last solid structure is metallic bonding. So yes, pure metals, pure gold, pure copper, that is a crystal solid. So if you have a copper wire, you have copper crystal in a wire form. So now the way a metal forms its crystalline solid, this is really different. This is called an electron sea model. So we have what's called a sea of electrons. Another term is called delocalized electrons. So essentially a metal, you just have plain pure metal again, not part of a compound, just plain pure 100% metal. Really what you have are these positive ions. And so this is like your nucleus, maybe your core electrons, but you have your positive ions here. Well, the valence electrons, so like let's say this atom over here has this valence electron there. Well, that valence electron doesn't just circle around its own element or its own atom. It'll actually move around. So it'll go wherever it wants, all over. All right. So it'll go anywhere it wants. So that's why you call it delocalized. This one electron we say is part of this atom is with any atom, goes all over. And then same thing, you have another electron here that can go wherever it wants, all over. So you got all these different electrons moving around, all delocalized, all moving all over the place. All right. So that's how a metal works. So yeah, so we say, oh, copper has, and we say, oh, well, copper has 29 electrons. Okay, yeah, when a single atom of copper has 29 electrons. All right, but again, if it has an entire metal, okay, those valence electrons and that's 29 electrons, those are actually moving all over the place through all the copper atoms around it. So just like that last line there at the bottom, they're not bonded to any particular atom. They're free to move about the solid. All right. So if you look at this, think about it. Yeah, that's pretty much tells you why metals have their own specific properties. They're different than all the other types of solids. Very good conductor of electricity. Because of all these electrons moving around, it's easy to have some sort of electrical source, pump it in this metal, and these electrons moving around, carrying that power, that force of electrons through to the other end. So that's why metals are a good conductor of electricity. All right. Same thing with heat, because of these delocalized electrons, they're really not set in place, so the atoms can move a little bit, can move faster and vibrate much easier. So that creates a lot more heat. That's why metals get hot readily. And also that's why metals are malleable, ductile. You can bend them into whatever shape you want. Because again, these molecules or these electrons are not set. They're not keeping those atoms on one set spot. So that is your metallic bonding. So those are your four different types of solids. You got the ionic solid, you have the molecular solid, covalent network, and metallic solids. Now, this is just a quick summary of the different solids and the different properties. All right, so solid types, molecular, atoms or molecules, just make sure they're all nonmetal. Types of forces, LDF dipolar hydrogen bonds. Properties, melting points are typically low. They are poor conductors because the electrons are kind of set in their covalent bonds. Covalent network, straight up atoms. Covalent bonds. They're very hard with high melting points, just like diamonds, just like quartz, because of those covalent shared electron bonds. Poor conductor of heat or electricity. Again, because the electrons are kind of set in place, and it's hard to get those atoms to vibrate. Ionic compounds, electrostatic attractions of positive and negative ions. Yeah, electrostatic mean you have a positive ion and a negative ion attracted to each other. They're very hard. They can be brittle, which means if you hammer it, it's going to shatter into a million pieces. It's not going to flatten like a piece of metal. High melting point. Yeah, table salt, the melting point of table salt is really super high, like 1,000 degrees Celsius, something like that. Poor conductor of electricity, unless it's dissolved. So that's a key there. So if it's dissolved, yeah, you have those free-flowing positive ions and negative ions. That helps in the conductivity, but solid ionic compounds will not conduct electricity. Okay, metallic, those are metal atoms, delocalized electrons, and yeah, metals are kind of weird because they can be soft or hard depending on the metal. Melting points can be low, can be very high. Something like copper, that's really high melting point. That's why we use copper for our cooking. Some metals like gallium metal, All right, element number 32. Okay, gallium metal will actually melt in your hand. Yes, it has a melting point of about 28, 29, 30 degrees Celsius. So it'll actually melt in your hand if you hold it in your hand. So yeah, so that's so those are different properties and different types of particles used for the solids.